When we look at data, our eyes are almost always drawn to the average. The average salary, the average temperature, you name it. But what if I told you that the average is often the least interesting part of the story? Today, we're going to dive deeper, way beyond the mean, to uncover the hidden shapes in our data that reveal what's really going on.
So let me start with a little puzzle for you. Imagine you have two sets of data. They have the exact same average and the exact same standard deviation, the same spread. So they must be pretty similar, right? Is it even possible for them to be telling completely different stories?
The answer is absolutely yes, and it's not even close. The crucial missing piece isn't the center or the spread, it's the shape of the data. And we uncover that shape by looking at what statisticians call higher moments. Think of it like going from a flat 2D picture of your data to a full-on 3D model.
Okay, so our first clue in understanding a distribution shape is a concept called skewness. The name kind of gives it away, right? This is all about measuring lopsidedness. Is our data perfectly balanced, or is it leaning heavily to one side?
So what is skewness really? Well, it's basically a single number that tells us two really important things: which direction our data is leaning and by how much. It's all about putting a number on that lack of symmetry in a clear, straightforward way.
Now here's where it gets really interesting. Look at how skewness messes with our classic measures of the center. See that middle row? In a perfectly symmetric, zero skew world, the mean, median, and mode are all best friends, living in the same spot. But introduce a positive skew, like in that top row, that long tail of a few super high values literally pulls the mean over to the right. And of course, the opposite happens with a negative skew, where a few low outliers drag the mean down to the left. It's a classic rule of thumb in statistics.
But, and this is a big but, that rule of thumb, it's not a law. As a 2005 journal article pointed out, this tidy little rule can fail with, and I quote, surprising frequency. This is especially true with more complex, real-world data. So while it's a great starting point, you can't just stop there. The true shape is often more nuanced. Asymmetry, though, is only half the story. To get the full picture, we need to look at another dimension: kurtosis. And if skewness is about the lean of the data, kurtosis is all about the tails. It's the tail of the extremes, the outliers.
So kurtosis measures the tailedness. What does that mean? It's not about how wide your data is overall. It's about how much of your data is packed into the extreme ends. A high kurtosis score is basically your dataset's way of telling you, hey, watch out, I have a tendency to produce some really wild results.
Now, to really get a handle on kurtosis, we need a baseline, a reference point. And our reference point is the good old normal distribution, the bell curve. The kurtosis value of a perfect normal distribution is exactly 3. 3 is our magic number. Remember it.
Because 3 is the baseline, statisticians came up with a clever way to make things more intuitive. It's called excess kurtosis. You just take the kurtosis value and subtract 3. Simple. This way, a normal distribution has an excess kurtosis of 0. If your value is positive, we call that leptokurtic, it means you've got heavy tails and you're more prone to outliers. If it's negative, platykurtic, you've got light tails and a distinct lack of them.
This leads us to a really common question, one you've probably heard or even thought yourself. You hear heavy tails and you think, okay, if the data is piling up in the tails, it must be getting squeezed out of the middle, right? So high kurtosis must mean a sharper, pointier peak, right? Well, get ready, because we are about to bust one of the most persistent, long-standing myths in all of statistics. The idea that kurtosis measures peakedness is, to put it as simply as possible, wrong.
And look, this isn't some new debate. This incorrect notion has been floating around for over a century. It actually goes all the way back to Carl Pearson himself, the guy who coined the term, when he linked it to flat topness way back in 1905. And for decades, textbooks and software have just kept repeating the mistake.
And this slide right here is the smoking gun. It shows exactly why the myth is wrong. It is entirely possible to create a distribution that has ridiculously high kurtosis but is actually flat on top. And on the flip side, you can have a distribution that's infinitely pointy but has very low kurtosis. The peak and the kurtosis value are just not connected in the way we've been taught.
So what is actually going on? The best way to think about it is as a movement of stuff, of probability mass. First, picture the shoulders of a distribution, that area about 1 standard deviation from the middle. High kurtosis happens when mass moves away from these shoulders. So where does it go? Well, it goes to 2 places, the extreme tails
and the very center. Now, while some of it moving to the center creates the illusion of a peak, the real heavy lifting in the kurtosis calculation, the thing that really drives the number up, is the mass shifting way out into those tails.
So let's put this to bed once and for all. Kurtosis tells you virtually nothing about the peak. Its only clear, unambiguous interpretation is about the extremity of the tails. It's about the outliers in your sample or the potential for a distribution to produce some seriously extreme outliers. It's about the tails, not the peak, period.
Okay, so we've busted a century-old myth. That's cool. But why does any of this, skewness or this whole tail business with kurtosis, actually matter? Well, it turns out that ignoring the shape of your data can have some pretty serious real-world consequences.
Let's start with the hidden trap you might not even know exists. Check out this table. The very tool you're using, whether it's SAS, SPSS, or even Excel, could be giving you a different answer for kurtosis because they use slightly different formulas. Now, for big data sets, the difference is tiny, no big deal. But for smaller samples, that choice of formula can seriously change your results. It's a silent bias you just have to be aware of.
And the applications are literally everywhere. In finance, assuming market returns follow a nice, clean bell curve can be catastrophic. They don't. They have fat tails, which is a statistical way of saying that massive crashes, those black swan events, happen way more often than a normal distribution would ever predict. Kurtosis is how you measure that risk. And in machine learning, oh yeah, it's huge. Models like linear regression assume your errors are normally distributed. If your data is super skewed, you're breaking the rules, and your model's predictions could be complete garbage.
Here's a really powerful way to think about this, something you can take with you. If you think of variance as measuring volatility, how much your data jumps around, then you should treat kurtosis as the volatility of volatility. It adds this whole other layer. It doesn't just tell you that your data fluctuates, it tells you how often those fluctuations are likely to be wild, extreme, off-the-charts events.
So the next time you look at a data set, I want you to ask yourself this question. Is the average that you're looking at telling you the whole story? Or, now that you know about skewness and kurtosis, is it really just the beginning of a much deeper, much more interesting narrative that's hidden in the shape of your data?